concept 4. It's on systems and system models. What is a system? Basically, a system is anything that's separate from the universe, and it allows us to study it, and it makes sense. Because in science, systems and system modeling allows us to understand phenomena, and in engineering, we can build systems, and by improving those, it allows us to improve design. And so what do we study in science? Remember, we study the universe. We try to understand how the universe works, but that's too big. And so how do we make sense of it? We divide it into what's called systems. And so a system is a portion of the universe that's separate from the universe. And it just makes it easier for us to understand how it works. And so how does a system work? Well, basically you can have forces that are applied to the outside of the system. You can also have matter and energy that move through a system or are recycled in a system, and we're going to talk about those more in the next concept. But basically you set aside this one system, and then you can use that to do your studies. And so what could be a system? An elephant is a system. So is a galaxy. So is a machine. So is a nuclei, or a fundamental particle, So is an idea. And so basically, if you have a system like this is a system that is going to show us how a frog eats. There are a few characteristics that they have. First of all, you're going to have a boundary. In other words, a boundary between the universe and your system. You're going to have components, or the parts. In this case, it'd be parts of the frog. You're going to have resources that move in, or matter that moves in, and energy that moves into the system. You're going to have flow of that material, and sometimes it's recycled, and then you're going to have some kind of a feedback mechanism that allows it to remain at stasis. And so, how does a frog eat? Well, you might have a mental model of how that works. You might know how a frog eats. You might think that, but the problem with a mental model is that it's just yours. It's internal, unstable, it's incomplete, and it's going to be different in every one of us. And so we don't use mental models when we're talking about science or studying systems. What we use is called a system model. A system model is simply a way that we understand how a system works. The nice thing about these is that they're clear, shared by everyone, and they're also external. So this would be a nice system model for how a frog is taking in energy. And so there are a few things that you should notice about models. Number one, or system models, is this idea of emergent properties. In other words, when we start at the very small, so this, for example, is a chlorophyll molecule, we don't see a lot of properties that will eventually become apparent as we move towards bigger and bigger systems. And so chlorophyll is going to be found inside a chloroplast. Once we get to the level of a chloroplast, there are going to be emergent properties, or in other words, properties that show up this level that didn't show up before. Or even as we move to a leaf, now we're taking in carbon dioxide that can be utilized by the chloroplast, and so now we even have greater emergent properties, or the emergent properties of a tree, or even a forest. And so to understand a system, we basically have to choose one level, but know that there are going to be things above that and below that that we don't necessarily see. And so what's the goal in a science classroom? We want our students to construct system models. So how do we start? We begin in the lower classes by doing drawing and then descriptions. We want to then include invisible structures in those drawing and diagrams. We then want to include mathematical relationships. And finally, we want to talk about the limitations and the assumptions found within those system models. And so what's the progression? Where do we start? Well, in the lower elementary grades, we want our students constructing system models right away. In other words, we want them throwing darts at a dartboard and getting better and better and better over time. And so a good way to start that is with a science notebook. You want students collecting data, and everything goes in the notebook. This is funny. This is from Apollo 17. Basically, when they sent them to the moon, they asked them to do drawings of the aurora. In other words, these coronal interactions as the solar radiation from the sun is hitting the moon, and they got all these phenomena, but these are pictures that the astronauts were actually drawing. And so that's a great way to start. Modeling is important as well, and so this would be an example of an activity you could do in lower elementary grades. You could give them some Lego pieces. You could then have them construct a model, and then you could come up with a description so they could hand those parts to somebody else and they could build that model as well. We want to start talking about invisible features as well. And so there's lots of things that you can't see. And those are things like forces or matter that's invisible. And so one thing that's between the two of us right now is carbon dioxide, but you don't see it, and so lots of times we don't think that it exists. And so a really important cycle that we have is called the carbon cycle. In other words, carbon in the atmosphere is going to be used by plants. That carbon becomes part of the plant, and if you eat a plant, then it becomes part of you. We then eat plants or things that eat plants, and that carbon moves into us, and so you're literally made of what you eat. And so we want students not only drawing systems and drawing system models, but we want them labeling things that you can see and also labeling things that you can't see. In this case, if you don't see carbon dioxide, you tend to think that it's really not there. As we move up into the middle school grades and then on to high school, we want to start talking about mathematical relationships. And so this is a climograph. Climograph is a way to look at the precipitation and temperature in a certain area, and so in a certain biome. So we could look at a desert and compare that to tundra, and so we could now start looking at mathematical relationships, ways to quantify the data. Everything in science is built on math, and so we want our kids starting to build those mathematical relationships as well. So as we build these models and they get better and better and better, we want our students looking at them, and we're looking for limitations or assumptions that we're making. In other words, this right here is the carbon cycle, and it's trying to quantify mathematically the amount of carbon at different levels. But it's just a model. It's a model for a system. It's not the system itself. And so we want our students using argumentation to talk about these systems as well, and where there is good evidence and where there is bad evidence as well. And then when we get to engineering, in other words, we want to get better and better and better at building these system models because they allow us to understand at least a portion of the universe. And I hope that was helpful.